So now we start to get into some of the unusual reactions that you could do with double bonds when you want to make something really specific. And some of them have pretty exotic reagents. This one has mercury in it. It's been around for a long time, and there's lots of modern ways to do this now, but this is still in use, and it's a really traditional reaction. So if you have a reaction that can rearrange, but you don't want it to, that is a problem. Because let's say you want to do this hydration of a double bond. Okay, so you've got your double bond here, you're adding H3O+, you want it to add using Markovnikov addition, and that's your desired product. However, when you do the reaction, rearrangement is really likely. So if you go through the mechanism, you can see that you're going to get a hydride shift, and the major product is actually going to be this one instead of what you want. So how do you prevent that from happening, and what can you do? And the best way is to do a hydration using a mercury reaction, and this is called oxymercuration. So this is an overall picture of it, and then I'm going to show you the mechanism in a little bit more detail. So oxymercuration, in this, the mercury it acts like the H+. The H+ in the HCl reaction that we saw earlier, mercury sort of takes the place of that. And what it does is instead of adding a hydrogen, it adds mercury. But then it still follows Markovnikov's rule here. But we don't want mercury in our final product, so there's a second step to this reaction, and that's called demercuration. And essentially what it does is it replaces the mercury with hydrogen, and it does a reduction there. So that the final product is the one that we wanted with no chance of rearranging. So the steps to this I'm going to show you are written out here. Mercury is a cation, and it acts like a proton. And then it makes what's called the mercurinium ion, which is really hard to say, which is kind of a bridged three-membered ring. And then the water comes in as a nucleophile. So here. So mercury acetate, which is Hg, and this is an acetate group. There's two acetate groups. It falls apart all by itself in solution, and it makes a mercury with a plus. And the only thing that we really care about here is that this acts like a proton. So overall, we've got the alkene. It attacks the mercury plus to make mercury attached to carbon, and it's going to make the more stable carbocation here, just like the proton did. And then the nucleophile is going to come in, and nucleophile is usually water, and it's going to give us a new bond here, and that's going to lead to the product. One thing to keep in mind, and we're not going to talk a whole bunch about it, but the mercury here is partially bonded to the carbon with a plus, and it makes this ring here. This is kind of like a resonance structure. This structure up here explains the product, but keep in mind that the mercury does make what's called a three-membered ring. This species here is what's called the mercurinium ion. So then we want to get rid of the mercury, and that uses a reaction that's called demercuration. We are not going to do the mechanism of this. It's actually really complicated, and no one ever talks about it, so we are not going to talk about it. And essentially what it does is it replaces the mercury with a hydrogen. Anything that adds hydrogen is called a reducing agent, so just keep that in mind. And sodium borohydride is one of the really, really common reducing agents. The hydrogens here are H minus, and so they reduce things really easily. And that just gets rid of the mercury, and it turns it into a hydrogen. So overall, what happens is you start with a double bond. The hydroxyl adds to the more substituted carbon, and it cannot rearrange. So this is a really good reaction to do when you don't want a rearrangement to happen. Like I said at the beginning, if the nucleophile is water, it's going to make the alcohol. This is by far the most common way to use this and the most common reaction when we talk about mercuration. Another thing I would just want to mention is that we're not drawing the middle step. We're just saying that this reaction has two steps, 1 and 2, and I'm only showing you the final product from step 2. And this is done a lot, especially when we have multi-step reactions, and we don't really want to draw every single step because it would just take too long and it would be really complicated. So like I just said, it's typical just to draw the final product when you have a multi-step reaction. And make sure when you do that you number your steps here, 1 and 2. If you don't number them, it will give the assumption that everything is put all together in one pot, and that's not true. So it can't rearrange here, which is you wouldn't want to bother to use mercury unless you really had to. So you wouldn't use this reaction unless you were worried about rearrangement happening that you didn't want to happen. So if you do this reaction with an alcohol instead of water, what happens is the oxygen is still the nucleophile, but now instead of making the OH, it's going to make an ether product. So whatever the oxygen is attached to is going to end up in your product. This is an ether. This would be called, a methyl ether. You could use, in theory, any small alcohol to do this. Instead of methanol here, you could use ethanol. I don't really see using anything much bigger. I think that would be really complicated. If you had, instead of an alcohol here, if you had a nitrogen, if you had an amine, then the nitrogen would add here as a nucleophile. Water is definitely the most common thing, the one up here, but you could add other things. Okay, so now I want you to pause the video, and as you come to each page, do the practice problems in your packet, in your notebook, on scrap paper, and figure out the products yourself, and then turn it back on and check and see how you did. Okay, so these two reactions are side by side. They're both the same reactant, yet if you do the just add water and acid for a typical hydration, you're going to get the rearranged product. If you add if you do the oxymercuration with water as a nucleophile, followed by reduction, and again, I haven't shown the intermediate here, then the final product is going to be the unrearranged product. Okay, so these are two more to practice. You see in red is the solvent that's the nucleophile. So instead of water, you could use ethanol, or instead of the water, you could use an amine. So figure out what these products would be. Pause your video, figure out what these products would look like, and then turn it back on and check and see how you did. Okay, if the nucleophile is ethanol, that's ET is ethyl group, then it's going to make an ethyl ether. And if the nucleophile is a nitrogen, then it's going to make an amine product. These are not so common, but they could happen.